So we also talked about optimization being a prescriptive analytics. So we mentioned that each mathematical model has four main components. One was the input data, which we call parameters. Those were the constants that we had in the objective function and right-hand side of the constraints. And then we had the decision variable. And then based on the decision variable, we wrote one objective function and a set of constraints. The objective function and constraints are all functions of the decision value. We also learned about the solution space. If you recall, we did something like this, and we had a feasible region. Any solution outside of that region would be considered feasible. And then there was one point that was the best. We call that exact optimal solution, and points that were near that, that would give a value to the objective function that is almost as good. We call those near optimal. And we just mentioned it in one sentence that if we call this a linear program, the models that we saw, but if the decision variables only take integer values, such as when we want to optimize the number of products we produce, those are, we cannot produce, for example, half a car. They have to be integers, 1, 2, 3, 4,000, whatever. If that's also a constraint, we call that integer programming, or IP, which is another thing we will focus on. But that one change in the decision variable makes it a totally different subject because everything we use in linear programming will not be usable anymore for integer programming. All right. I also formed your teams. Can you see? So first name, last name, email, team number. We have 5 teams of 5 now. Only 24 students responded to the survey, but on Bronco Direct, I see 29 students. I don't know why. So if you can, I don't know, but half of you or some of you are online. I don't know what's the best way to sit next to your teammates. We will have an activity. So we'll come back to this, and basically, I want you to sit next to your teammates, and I'll give you a problem to solve together. All right. I tried to have each role in each team. A lot of you were enforcers, so it wasn't easy. But I think we have enough of each, at least as a second preference. For example, if your team doesn't have a first preference facilitator, there is a second preference of that. We will come back to this. But for now that you're warmed up about modeling, this is very similar to a model that we solved last week about the gas. Remember, we viewed an oil company that could produce jet fuel and just send gas to another plant. This is similar to that. So quickly read over the problem description. Try to see if you can quickly formulate this. Do you remember the thought process, how we go about modeling? The first thing we think about. Do you remember what that was? Objective function is usually clearly given to us. Write a model that maximizes this or minimizes that. That usually tells you about what is the objective function. But decision variable is what the solution will be. Decision variable is the container of the solution. So you want to think about that as well. So start thinking if I solve this and I want to give the solution to the company to actually start producing, how do I present that? And then what decision variable can contain that table of solution? Okay, start working on this and reading it. If you complete it, let me know. How it happened. Okay, anyone? So input is what? Data parameter. It's given to us. So we have two types of cell phones we want to manufacture. Model 1, Model 2. Each one gives us the revenue and has some cost. Obviously, cost minus revenue gives us the profit. And I think we are trying to maximize the profit. That one is easy. Always straightforward, right? You know that we're gonna write maximize z equals something, a function of the decision value. But then I need the decision value to be able to write that. So what do you think should be the decision value? So after you solve this, like what is it that they don't know? And they want to solve a problem to find what? Yeah, number of phone models, how many model 1 to produce, how many model 2? Let's say you have the answer. Model 1, 300, model 2, 500. You represent that with a table, right? First column, model name, second column, the values. So the values come in one row, right? If there is one row, it means that it's one dimension. So you just write it with xi, x1, x2. If it's two rows, it means that two-dimensional, xij. All right, so I can just write xi. Do you hear this too? It's very annoying. I don't know how to do it. So number of model I to produce, and I is 1 or 2. So x1, x2. x1 number of model 1 to produce, x2 number of model. And then objective function, that's it, is maximize z equals, how do I write that? I'm gonna produce 800. Some model 1 plus some model 2. What is it? 800. 800 minus 500. That's how much profit I get from, I'll have from model 1, and then here 920 minus 600, right? Then this objective function. So if you give this to the computer and ask it to solve it, what's going to be the answer? Infinite. So we want to restrict it so that it doesn't go through. Why should we restrict it? Because our resources don't allow producing infinite number of phones. Either it's the demand or the resource that we have. So that's subject to, that's one resource that we have. Our labor should be less than or equal to 240,000 hours. How do I write the amount of hours that I'll consume based on X1 and X2? 3X1 plus 2X2, right? Is there any other resources or conditions or limitations that I have? It says model to produce should not exceed 60% of total production. What is total production? What is it? How many will I end up? If I produce X1 model 1 and X2 model 2, how many will I produce? X1 plus X2, right? And I should not exceed that 60% of that. 60% of that, X2 should be less than that. Does it make sense? So I rewrote that line, the number of like that. Anything else? Oh, X1 plus X2 at least. So why didn't I, for the previous one, for the previous constraint here, why didn't I just write X2 less than or equal to 60,000? The 60,000 is 60% of 100,000. Why didn't I do that? Or should I do that? What do you think?
Sure.
Yeah.
Should X1 plus X2 be greater or equal to 100?
Oh, it says at least, right?
Yeah.
Yeah. Thanks, Marcus. So what do you think?
Because it is at least, so we cannot.
Maybe we produce more.
We can produce more.
Maybe, yeah, if that's the minimum, maybe what we end up producing is more than that. What if it's the maximum? What if the problem is that you should not produce more than 100,000? How about that?
Depends. If the problem says then we have the liberty of producing less, then the number is not stated.
The liberty, though, if you're talking about liberty, I want to maximize. So the more I produce, the better. So shouldn't I just produce 100,000?
In that case, we can.
Maybe this constraint on the labor doesn't allow that much. If it's a maximization, if it's a lower bound, upper bound. Maybe with there is a constraint that the combination of this I won't be able to produce 100,000 total, right? Maybe it's 99,452. That's the cap. Maybe 100,000 is outside of the feasibility. Does that make sense? Okay. And as usual, we write X1 and X2 should be positive, and here they should be. I write X1, X2 belong to integers positives instead of writing that, which makes it an integer programming problem. So we just modeled it, we haven't solved it. Any questions?
How are you writing
X1, X2 in a member of Z. It's like bold-faced Z positive. Which reminds me that my handwriting has not improved. X1. Or better way is this. Xi is a member of not much better. And here I write for all I. For any I. 1, 2, 3, 4.
I mean, so that makes it an integer programming problem.
Yeah, because the variable is integer, now it's an integer programming problem. Which we don't deal with right now, but later on we'll see how we can solve them. Okay, this one. So in the modeling aspect of OR, you will see that it's like art. Like every model, you have to be creative, figure out how to write the mathematical equations or inequalities to describe this. So this is the same as that description, but this is very precise and computer understand. I don't know if AI can do it now, but even if AI reads that, it has to first make this, then solve. Okay, so we need this anyway. I don't think AI can figure this part. All right. If you're good here, so the next few problems that we're going to see, they're all different. Every time you see something new, so the models you have seen before will not work. Okay, but it doesn't mean that you're not understanding. It means that you're learning if different models, and then models that you will see later on is probably similar to one of these. Then you just change that to make it look like what you're working on. So how about this? Read and see how we can model this. A hospital needs to schedule nurses so that can satisfy the projected weekly demand. That table shows that, the demand. Mondays, we need 5 nurses, Tuesdays, we need 6, and so forth. There is a condition. If a nurse assigned to work on Monday, sure he will working on Monday, Tuesday, and Wednesday. So 3 consecutive days. So if you hire them for Wednesday, they're gonna work Wednesday, Thursday, Friday. Sunday, Monday, Tuesday, and so. That's the only condition. And your objective function is what's the minimum number of nurses that the hospital needs to hire to satisfy demand? How many constraints do we have before even formulating? Like how many conditions we have? 1, which is 3 consecutive days. That's one. Another one is satisfying the demand. Because if you ask the computer without the constraints, what's the minimum number of nurses? It says 0, right? But then we say, okay, well, we need to have at least these many. So another condition is, another solution is, okay, hire 5, 6, 7, 6, and some of these. But is that optimal? Because you could have used the 5 that you hired here in these 2 days. Why are you hiring 6 more again? So you want to think about decision variable. What is the first thing you think about? How do I present the solution after I solve it? So after you solve it, you give them a schedule, right? Hire this many for Monday, who will start on Monday, this many will start on Tuesday, and so forth. A table. No, Monday, Tuesday, first column, second column, how many you're gonna hire for that day, right? So just like the previous one, it's gonna be X1, X2, X3, X7. We have 7 days. Okay, start working with that, see if you can model it. At least the objective function. What do you think about objective function? So how many do we start? Do we end up hiring? Anyone? Say that as a function of x1, x2, x. So we hire x1. We don't know how many. That's why we call it x1. It could be 2, 3, or 4, whatever. We end up hiring x2 for Tuesday, x3, x4, x5, x6, x7. So they could be any number. Could be 5, 6, 7, 4, 2, 3, but it should work. And with the constraints, we will make sure that it works. It satisfies the demand. But some of those excess is how much we end up hiring, right? X1 plus X2 plus X7. And I write that as sum of I goes from 1 to 7, Xi. Subject to satisfy the demand and make sure that no one works more than 3 consecutive days. Works exactly that much.
And if it says that they need to work 3 consecutive days, does that mean they can't work 4 consecutive days?
No, it's like the limit. And you want to as employer, you want to maximize how much you utilize your resources, right?
So they can work for 3 consecutive days, but
Mhm.
not for 2 consecutive
Not-
days.
For two, maybe if you have too many of them, but you cannot. So this is a. You always want to maximize the use of your resources, right? If your solution hires people who work only 2 days, it means that it's not a very good solution, right? But also, you want to make sure that you do not make them work more than 3 days. And I'm going to give you a hint. Write a constraint for each day. The demand for Monday, 5, 6, 7, 8, 10. You want to make sure that you have at least 5 people for Monday, 6 people Tuesday, and so forth. How can you arrange those x1 to x7 here for a constraint? Who works on Monday? What is it? Hmm? The ones who hire on Saturday and Sunday also work on Monday. And people you hired on Monday for Monday, right? So x1, I mean x6. Yeah. I have to write it like this. X1 plus so these are basic. I'll tell you why I wrote it like that. X1 plus x6 plus x7. Those are people who are eligible to work on Monday. Next one, what do I write for Tuesday? Same logic. Who's gonna work on Tuesday? Monday, and also people who work on Sunday. Okay, so x1 plus x2, Tuesday ones also, plus x7. How about Wednesday? Right? And then Thursday, Tuesday, Wednesday, Thursday, and then Friday is gonna be 1, 2, 3, 4, 5, 6, 7. Monday, Tuesday, Wednesday. Oh, that's 4. Here. Does it make sense? Again, I have to make sure that xi is integer and positive for all I. How many constraints do I have? 7 here. How many here? 7. Whenever you see for all, it means that you have to repeat this for every I. So x1 is integer, x2 is integer, x7 of them. 7 there, 7 here, 14 accounts. Good. This one. Next one, someone will model it. Okay. It's gonna be different, but sure you can. So what part of it so far is a little confusing? Or what is confusing, if there is anything?
How for me identifying how to go about writing that.
Yeah, it's like a creative process, right? How to work with all these variables, write it. But the important part was this part. Because you know what, these are like the components you want to make this with. If you don't know what are the components, it's even more difficult. So the first step, what decision variables can contain the solution. Here, x1 tells you how many to employ from day one, x2, and so forth. All right, are we good? Next one. Investment. Can you read back there?
Yeah.
You have it there too, right?
Yeah.
An investment company currently has $2 million fund to invest in 4 possible categories: bonds, options, stocks, and savings. Company would like to keep the total risk associated with the investment less than 6%. That's one thing. That sounds like a constraint. The average risk is calculated by dividing the expected risk over the total money invested, not including the savings. If you just get the decision variables, the rest is gonna be easier. What do you think? Decision variable is basically unknown. What is it that's unknown and we want to find it? Money invested in each category, right? So if I solve it, how do I show that?
X,
What is it?
XI is the dollars to invest in category I.
Yeah. Exactly. Which could be fractional too. Money to invest in category I. Okay, I have that. And it says, how much the company should invest to maximize earnings. So objective function is maximize something equals to, how do I write the earning based on these guys?
Risk percent.
10% of X1 plus 15% of X2 plus 20% of X3 plus 2% of X4. And I want to summarize that. Let's call this E1, E2, E3, E4. EI, XI. 1, 2. Does it make sense? So if I give this to the computer, it tries to maximize its x's and goes to infinity, right? The more the better. There is nothing that stops it. So I have to subject this function to the constraint. What is the first constraint? The budget that you have. You cannot invest more than the budget that you have. So X1 plus X2 plus X3 plus X4 should be less than or equal to 2 million. Another one is, it says, the company would like to keep the total risk associated with the investment less than 6%. How do I write that?
X1 plus X2 plus X3 less than 6%.
It says, you can see that how to calculate the average risk.
Mm-hmm.
So if you multiply the risk percentage by each investment and then divide that by the total dollars invested, that should be less than 6%.
First of all, there is a chance, is there a chance that we do not invest all of that?
Yeah.
Yes, but because this is a maximization problem and we don't see anything else, yeah, maybe. Because of the risk, we end up not investing all of it, right? So let's say, but because one of them has a 0% risk, maybe everything else goes to saving, right? So I think the optimal solution, in the optimal solution, some of the excess is going to be 2 million. Because common sense tells me this one has a 0% risk. So invest most of your money in high earning categories and whatever left is left, instead of just keeping it, this one gives you 2%, 0% risk. Just put it there. So it doesn't make sense to have a solution that has any leftovers. But that's more, we will do this type of analysis later on. For now, there is a possibility that the optimal is not 2 million. So let's formulate the risk, and at the end, right, less than or equal to 6%. What did you say for formulation?
So the risk percentage multiplied, so like basically that same summation of I equals 1 to 4 of RI, I guess,
Mhm.
XI, divided by the summation of investment.
Summation of investment is gonna be x1 plus x2 plus x3 plus x4. And then this is going to be 8 x1 plus 5 x2 plus 10 x3. 0 x4, so I don't write it. And the values are going to be positive, so xi greater than or equal to 0 for all I. It's good now, however, it's called linear programming, so we want to stay away from any form of non-linear expressions, which in this case, it's not essentially non-linear, but we want to make it at least look like linear. So that part where I have division. So I'm gonna rewrite that part as I'm gonna multiply each part by sum of x's and then bring them all to the all values to the left hand side, then rewrite it. If I do that, I think it's gonna be 7 point. Are those? Let's make that just 6. X1 plus minus x2 plus and x3 I just rewrote that one, replaced it with this.
Why is it greater than or equal to zero?
Why isn't it greater than?
Or why is it less than or equal to zero?
Because that one was less than or equal to 0. And some of these numbers is positive. I'm multiplying each side by a positive value.
I thought that was less than or equal to 6. Because you're looking at.
Yeah, but if I multiply each side by this, the right answer is going to be 6x1 plus 6x2 plus 6.
Got it.
And then I subtract them from the left. That's what I end up with. So multiply each side by.
Hello, Professor.
Yeah.
I think 10x3 is 10x3 minus 6x3. So it's 4x3. You write down 10x3 in
Oh, yeah,
finally.
yeah, you're right, you're right. I thought about 4, but I wrote 10. Thanks. It's good. It seems that it's working. Someone talked from a space. And so let me see how many we have on line. 1, 2, 3, 4, 6, 7, 8. 10. Here you have 13, 15, 18, 21, 24. Yeah. I don't know. I don't know why I see 29 students on. All right. Now let's have a challenge. And then take a break. Read this one. Just tell me what's going to be the decision variable. Just that. All right. Nothing else. What?
Which value?
Decision variable. Just tell me what's a good decision variable for this problem. So we want to see how many of each station each company is going to take, and the capacity of each company is given, number of people on each station is given. Let's say these are 3 different buses, or shouldn't be. The wording of these problems is a little weird, but the idea is these 3 buses are going to take these many people from each station. Take them to Rose Bowl or something. Or campaign of Trump or Biden. We give you a bus, and then drinks. So if we solve it, what do we say as the solution?
A schedule of which bus at which station.
Is it a routing problem?
It's not, is it routing? Does it say like how to go to the destination or which places to visit? Like what is it? Yeah, that's why the solution is important. Like, what should you say after you solve it? Like, hey, I solved it. This is what we should do. What is that thing that you should do or they should? The cost is the cost is given. We want to minimize that. So we give the cost as a property of the solution, which is this solution I'm giving you is the cheapest cost. What's the cost? Only like $90, right? But what is the solution? Like, what's the schedule? What's the plan? What is it that we should do that if you do, your cost is gonna be $90 or whatever? It's sort of like an assignment, right? Or allocation.
We have to determine how many people will go in a particular shuttle from a particular station.
How many
So
people,
that it.
how many of these 35 go with this shuttle? How many go with B? How many go with C? Right? In a way that all of them are taken care of. And the capacity of each one is not, we don't go over the capacity. Okay, so can you say that again? I want to see how we can put it in a table.
We need to figure out which company will pick how many passengers from which station so that it fulfills the capacity as well as the demand.
So what do you think we should present that in the table? What type of table? Something similar to the table we already have, right? instead of cost, we just put how many. Right? So instead of saying, instead of filling it up with costs and capacity, I just write A, B, and C, and here I was station 1, 2, 3, and I say how many each one takes. Right? It's a 2 by 2 table. So if I call this I, 1, 2, 3, and I call this J, 1, 2, 3, so over there. I can say Xij, number of people, company. I takes from the station J. Does it make sense? Which will be the entries of here. For example, X2, 3 is 5. X2, 3 is 5, which means company B takes 2 people from a station 5. But we don't know if it's 5. We have to solve it then. It will be populated with the correct solution. So this is one solution. Let me just fill it out with the solution. Let's say I need 30, I have 35 people here, okay. 20 go here, 10 go here, 5 here. So I've satisfied 35, and I haven't gone over those guys. And then I can put another 5 here, another 5 here, 0 here, and then I can put 4 here. 6 here, 0. That's a solution, right? But someone else could have, so in this solution, x11 is 5, x23 is 0, x33 is 4. Someone else could give me a different solution. And and there are so many different ways I can fill out this table, which means I have so many different solutions here. Some of them are infeasible, some of them are. Is this one feasible?
Will it form a matrix?
Yeah, it's a matrix. Yeah, but that's the meaning of Xij, right? And then I need to write the objective function based on Xij because these values are not known. These are variables, these are unknown. That's why we're solving it, to find those values. Find the value of the value. So I need an objective function that is subject to some constraints. What is the objective function? Based on Xij. What am I trying to achieve? Transportation cost is minimized. How do I formulate the transportation cost based on Xij? Minimize D equals how many people company A takes from a station 1? X11. We don't know how many, but it's going to be in X11. X11 is the container that's going to have the number of people company A takes from a station 1. So X11. What's the cost of each person? 15. Plus 13x12 plus 11x13 plus x21 plus and some of those. But I'm going to write it as summation of I goes from 1 to 2, j goes from 1 to 2, Cij xij. That looks confusing, but very easy. So Remember, these were Xij, these are Cij. C11, cost of taking one person from company one from a station. So this is C11, C12, C13, C21, C23, C23. So minimize this problem. If I give this to the computer, what's going to be the answer? These are all the zero. Don't take anybody, save all your money. But there's a constraint that says you cannot do that. What are those constraints?
Demand.
The demand. Okay. Let me write the demand. So this is subject to demand for station one. Some of these should be greater than or equal to 35. What are those? X11 plus X21 plus X31 should be greater than or equal to 35. What's the next one for this? Station 2, station 3. What's that?
X12 plus X22 plus X32.
The third one.
X13 plus X23 plus X3.
Anyone who takes people from station 3, company 1 from station 3 plus company 2 from station 2 plus company 3. Okay, now give this to the computer and ask it to solve it. What does it say?
So I have it taking greater than or equal.
It says, first of all, I'm not going to do anything greater than. I'll just do the equal. I'm not going to take any extra people. All right. And it says, okay, these three have to be greater than or equal to 35. I'm trying to minimize the cost. Who's cheapest? 13. So let's make X31 35. And the other two X's, these two 0, this 35, because it's the cheapest, right? But is that feasible? There's a capacity for company 3. So I'm gonna add 3 more variables, 3 more constraints. Company 1, company 2, company 3. Don't go beyond 30 or 20 for company 2, 24 for company 3. And what X's come here, show here. All the amount that company 1 takes, which is X1 from 1, company 1 from 2, company 1 from station 3. Same here. X21 plus X22 plus X23. X31 plus X32. Okay, now I give this to the computer. It should be good now, right? We took care of the demand, we took care of the capacity, and we have an objective function and solve it. For this problem, it won't happen, but if any of those was fractional, it would give half a person here. Because the computer is stupid, right? You have to tell them everything. Like, okay, Xij is integer and positive for all ij. We have a model now. And this model has a lot of applications, like a lot of problems you want to solve. You see that it's similar to this. Whenever you're trying to distribute, we call it a transportation problem. Whenever you have sources and supplies and destinations, you want to send them to different destinations. You don't know how much of each origin to send to destination. That becomes like a power company. You have different power companies. You don't know how much power should go to different cities, right? Each city has a demand. Each power plant has a capacity. That's a transportation problem. Anytime you see something like this, one little thing, and then let's take a 10-minute break. That one little thing is, I want to rewrite these guys as one constraint, similar to for all. You see a pattern here. Each line has the same index for the first index is the same in each line. We agree? So I can write sum of x. This is the fixed one. I, j, and then the j changes. So I put it on the summation. J goes from 1 to 3. Should be less than or equal to the supply of company I. And I say repeat this for each company or for all companies. Repeat for all companies, repeat this. So if I ask you how many constraints is this, it's 3, because for all I, and how many I's they have? 1, 2, 3. Okay, we want to get used to writing constraints like that and reading them.
For companies or for stations?
These are for companies, and for stations, I'm going to do the same. Let's do it then. These guys, I'm going to rewrite them. What does repeat in each line? The second index. X1, 1, X2, 1, X3, 1. Here, it's 1, 2, 2, 2, 3, 2. Whatever that's repeated in every line, you say for all j, and then here write x I j, and then summation is I goes from 1 to 3 x I j should be greater or equal to the demand of a station j. Station j. We'll come back to it. I'll give you some exercises so you get used to it.
Notation to the left corner, yeah. Greater, less than or equal-
Summation j goes from 1 to 3 x I j less than or equal to s I
That's,
for all I. For all is just like that inverse A, right?
it stands for the
That's for each company.
company.
I is each line,
Oh,
each row, sorry.
so the DCI or
So this is gonna be I because each row is I.
no, the S should be C or should be S?
This
Yeah.
S, which is supply, you
That's
guys.
supply.
This is S1, S2, S3. Let me write.
Thank you.
Oh, good question. That's this is Too many things. One page.